This week we're going to keep studying energy, and we're going to specifically look at the conservation of energy. So when you see the word conservation, I don't want you to think like in terms of the environment, like a conservation group is very concerned with preserving the environment and, creating environmental protections. That's not what we mean by conservation here. When we talk about conservation in physics, we mean that the quantity that we're talking about, so in this case, the conservation of energy, we mean that energy cannot be created or destroyed. Energy is always conserved. That means however much energy you have initially, you have that same amount of energy later, even after other things have happened. That's what we're talking about with the conservation of energy. And this week, we're going to specifically also start looking at another type of energy called potential energy. So let's just remember what we said last week. Of all the different types of energy we talked about last week when we were introducing energy, we talked about thermal energy, chemical energy, electromagnetic energy, nuclear energy, and we also talked about mechanical energy. So this is the main type of energy we're going to focus on this semester. Anytime something is moving, it has mechanical energy. Anytime something might move, it has mechanical energy. So we say that there's two types of mechanical energy. One is kinetic energy, and we talked about that a lot last week. That's the energy of motion. And this week we're going to focus more on potential energy, which we call the energy of position. So just to remind you, anytime something is moving, it has kinetic energy. Now we can think about potential energy. A nice way to define that is anything that might move if you let go has potential energy. So if you're holding something in a certain position and the position that you're holding it in, if you let go from that position and the object will move, then just being in that position gives that object what we're going to call potential energy. It's kind of nice to think of potential energy as being like something is in a position such that it has the potential to move if you let go. It has the potential to have kinetic energy. Okay, that's kind of a nice way to think about what potential energy is. So we're going to define total mechanical energy with a big capital E. So this variable here represents total mechanical energy. And our total mechanical energy is equal to our kinetic energy plus the new thing here is U is going to represent potential energy. So again, this is our total mechanical energy. K is our kinetic energy, and U is our potential energy. K is just what we learned last year. That's equal to 1/2 mv squared. And U, we're going to calculate that in different ways depending on what type of potential energy our object has. So there's a couple different ways that objects can have potential energy. Remember, I want you to think that potential energy is due to an object's position, and because of the position it's in, it might move if you let go. So let's consider something like a bow and arrow. So when you have the arrow notched on the bow and you pull it back, you're putting that arrow in a certain position where if you let go, then the arrow will gain kinetic energy. So there is potential energy stored when you pull the string of a bow back. You are storing energy there. And that type of energy is called elastic potential energy. This is the same type of potential energy that is stored in a spring, and we'll talk about that in a few videos. Another type of potential energy is electrostatic potential energy. And this occurs when you have a separation of positive charges and separated from negative charges. You'll learn next semester that positive and negative charges are attracted to each other. So if you separate a positive charge from a negative charge, there is potential energy stored there because if you let go of one of the charges, it will move towards the other one. So due to the way that positive and negative charges behave, they can store potential energy. But we're going to focus on this one next semester, so we're not going to talk any more about this. Another type of potential energy is called gravitational potential energy. And if you think when someone is standing up here, they have the potential to have a lot of kinetic energy. If they just take a step off, then they're going to start to gain kinetic energy as they fall lower and lower and lower. So objects that might fall downwards have what we call gravitational potential energy. And this is the one we're going to focus on right now. So let's look at how we can calculate gravitational potential energy. It's a pretty simple formula. So the big capital U means that we're talking about potential energy. The G here is just a subscript. It means we're talking about gravitational potential energy. because later we will distinguish between elastic potential energy and gravitational potential energy. And potential energy due to gravity is just equal to m times g times y, where m is the mass of our object, g is 9.8 because we're on Earth, and y is the y position of that object. So you see how the potential energy depends on the position of the object. The higher up the object is, the more potential energy it has. So let's take a second, read through this, and try to figure out how to rank the potential energy of these 4 positions of this ball. So we want the smallest to the largest, and I can just recall my formula for gravitational potential energy. These are all the same ball, so they all have the same mass. We're on the same planet. We're all on Earth. So really we're just ranking which one is the highest. C is the highest off the ground, so its Y position will be the biggest. So when the ball is at this position here at the top, it's going to have the most potential energy. B and D are at the same height, so they have the same amount of potential energy. And A is the lowest one, so that has the least amount of potential energy. And now I want you to rank the kinetic energy. So this is an object that's thrown straight upwards, and I've just shown you 4 different positions that the ball is in as it's thrown straight upwards. So think about what happens to the speed of the ball as it's thrown upwards, and then rank for me the kinetic energy of the ball in each of these 4 different positions. Well, we can recall our formula for kinetic energy. It's just 1/2 mv squared. So wherever the ball is moving the fastest is where it has the most kinetic energy. I know that when it's at the top, it's not moving at all. So up here, the speed would be 0. So the kinetic energy up here is 0. And I also know that as it travels upwards, it slows down. So this is right after it's launched. It's going to be going the fastest here. As it travels higher and higher and higher, it slows down. So B is going to be lower. So no matter what, we know A should be the biggest, C should be the smallest. And believe it or not, B and D are the same. You might be able to guess that because we know that that Y trajectory is parabolic with respect to time. So you know the shape of that curve should be parabolic also. But we're going to be able to prove that the speed at this position and the speed at this position are the same. We're going to prove that soon.